Recently, we've talked about the ability of gas to occupy the entire container due to its particles moving all the time. As the particles travel across the space of the container in the straight line motion, they eventually hit the wall, bounce back from it, and continue to travel in the opposite direction. All the smashing of molecules into the walls create the pressure of the gas. The more collisions of gas molecules into the walls, the higher is the pressure exerted by the gas on the container. So, let's see how change in the volume of the gas will affect the pressure. Currently, the volume of the container and consequently the volume of the gas that occupies it is 950 liters. If we push on the piston, we will force the gas to contract and occupy the smaller amount of space. Notice the change in pressure. Decrease in volume of the gas led to increase in pressure. Why did it happen? Well, inside of the smaller space, the molecules have to travel shorter distance before they smash into another wall. The sheer number of collisions of molecules of gas into the walls of the container increases. The more collisions of the gas molecules into the walls, the higher is the pressure exerted by the gas on the container. If we continue to decrease the volume of the container and through that the volume of the gas, we will see the corresponding increase in pressure of the gas. Now, let's expand the container and thus increase the volume of the gas. We can see the expected decrease in the gas pressure. So, when the volume of the gas is decreased, the pressure of the gas goes up. When the volume of the gas increased, the pressure of the gas goes down. So, the pressure and volume of the gas are inversely proportional to each other. Inversely proportional variables. If one variable goes up, another goes down. So if we build a graph of volume of the gas versus its pressure, it will look like this. When volume is high, pressure is low. When volume is small, corresponding pressure is high. Here in this table, I collected the data from the gas simulation, the volume of the gas and its corresponding pressure. When volume is high, the pressure is low. When volume is low, the pressure is high. So the product of pressure and volume will be the same number in any moment of the experiment, which is what a British scientist Robert Boyle discovered in the 17th century. Robert Boyle discovered the inversely proportional relationship between pressure and volume of a gas when the temperature is held constant. And this is the formula that we will be using in our calculations. Let's see where and how we can apply it. A 4-liter sample of gas exerts a pressure of 2 atmospheres. If the gas is allowed to expand to a volume of 16 liters, find the new pressure of the gas. Let's see. Our initial pressure of the gas is 2 atmospheres, and initial volume is 4 liters. Okay, we're allowing our gas to expand to a bigger space. The volume is increasing. It becomes 16 liters. So what is the new pressure of the gas? First of all, let's make a prediction. We increased the volume of the gas. We allowed the gas occupy a bigger space. So it means that we should expect our new pressure to be lower. We expect our pressure to drop. So let's plug in the numbers into our equation. We're solving this equation for the new pressure P2, which comes out to be 0.5 atmosphere, which is lower than our original pressure of 2 atmospheres. And that is exactly what we expected. A sample of gas under a pressure of 822 kilopascal has a volume of 312 centimeters cubed. The pressure is increased to 948 kilopascals. What volume will the gas occupy at the new pressure, assuming the temperature is constant? Here, our independent variable is pressure. Pressure is changed. how this affects volume of the gas. While pressure of the gas went up, we should expect the volume of the gas to go down from its original value. So let's plug in the numbers. We are solving this expression for new volume, V2, which comes out to be 271 centimeters cubed, smaller than the original volume. At 25 degrees Celsius, gas in a rigid cylinder with a movable piston has a volume of 145 milliliters and a pressure of 125 kilopascals. When the gas is compressed to a volume of 80 milliliters, what is the new pressure of the gas if the temperature is held at 25 degrees Celsius? So we see our gas first at certain volume and pressure, and we are asked to calculate the new pressure when the volume was decreased from 145 to 80 milliliters. So volume went down, so we expect the pressure to rise. Let's plug in the numbers and calculate for the final pressure, P2, which comes out to be 230 kilopascals. It is a very well expected increase in pressure that was supposed to accompany decrease in the volume of the gas. The fact that the temperature was kept constant was underlined in all three example problems that we've looked at. Increase or decrease in temperature has its own effect on the pressure of the gases, as we soon will be learning. But for now, however, we will keep the temperature the same to have a clear picture of how volume and pressure of the gas are related to each other. Now it is your turn. Pause this video and apply the formula of the Boyle's law to solve these problems. One piece of information that you might need to solve problem number 3: the phrase standard pressure refers to the pressure of 1 atmosphere. To recap on what you've been learning today, as the volume of the container increases, the pressure of the gas decreases. As the volume of the container goes down, the pressure of the gas goes up. The volume of a sample of gas is inversely proportional to its pressure if the temperature is held constant. And here is the graph of volume versus pressure of the gas, which has classical inversely proportional graph form.